Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in this video we will see type of structural joints. So our topic will be type of structural joints, then symmetric maneuver load, and next gust load. Okay, so that's the first type of structural joint. In general, aircraft component fabrication entails joining one part of the component to another. Means in aircraft, one part is connected with the other part. So that is almost everywhere one part is connected to the other part. So now the thing is how to connect that one. It's not like that we can fix or we can use by any method and that can be used. So how the parts are connected, just see, for example, fuselage skin are connected to stringers and frames. So fuselage skin, okay, is connected with stringer and frames, while wings skin are connected to stringer and wing strip. So just see here, the fuselage, both are same. So fuselage skin is connected with a stringer and frame, and wing skin are connected to a stringer and wing rib, unless the stringers are machined integrally with the wing skin. If a stringer is machined integrally with the wing skin, and in some more military aircraft with high wings loading, in case of like military aircraft where in the wings itself they are putting artillery and all, and these things, right? So for that case, wing rib is not used. In that case, again the frame is required. Okay. With the advent of all metal aluminium alloy construction, riveted joint becomes the primary method of connection. So the combination of metal and aluminium, any metal like zinc, copper, aluminum, okay. So any metal with the aluminium, after making the alloy of that one for the construction, riveted joint become the primary method of connection. So means when we are using metal and aluminium alloy, any metal with the aluminium alloy of that one, then riveted joint becomes the primary method. That is, riveted joint is the best option for connecting the things, with some welding and more recently some glued. So with welding, although aluminium alloy are difficult to weld, though aluminium alloy, whatever the aluminium alloy are there, that is difficult to weld, still we are using that only because that is more stronger compared to the other option. More recently, some glued joints are that used epoxy resin. So some are there when you can see that when you are making that UAV and all, right? There one glue type is there, you are just putting that glue and fixing. So that is the resin glue. In this section, we will focus on the most common method of connection, that is riveting. Okay, so we will see here the riveting one. In general, riveted joints are stressed and complex ways, and accurate analysis is frequently difficult to achieve due to discontinuities in the joint region. So what happened? Riveted joints are stressed in more complex way. Now the stress is there or here. Okay, I'll just see you. Like this is there. So here rivets are there, right? That depends on what are the shapes of the rivet. Generally, we are preferring the circular one only. So now here what happens? The stress will act from all the direction, right? At the top also. And the thing is, this one is discontinuous. Continuously from here to here we are not using. So for finding here the stress is also difficult. Okay, especially in complex structure. Okay, and accurate analysis is frequently difficult. So here we cannot get the accurate one also just because of their discontinuity in the joint region. Because wherever it's joining first, that to remove, you have to remove that part, you have to make the hole, and then you have to find. So through the structure directly we cannot find. Why? Because that structure is not continuous. Now there inside hole is there. The assumptions about joint behavior are fairly crude, but when combined with experience, safe design are produced. So when with the experience, where to put these rivets, how to fix that one, right? If that is happened with the experience or by the experienced person, then safe design can be achieved or safe designs are produced. Okay, now next is symmetric maneuver. The first one is the procedure. Okay, then so first the following provisions apply to the analysis of the maneuvering flight condition specified in paragraph B and C. So paragraph B is here and C we will see in the next slide. In this is there. So first, when a control is specified for sudden displacement, the assumed rate of control surface. So just see here this one. When a control is specified for sudden displacement, means if sudden displacement is required, okay, that the assumed rate of control surface displacement may not be less than the rate that the pilot could apply through the control system. Means the rate fixed, okay, for the control system which pilot can be used. The rate of displacement of the surface should not be less than that one. If less than that one is, that means that is not in the control of the pilot. Okay, then pilot cannot control that one. The effect of corresponding pitching velocities must be considered when determining elevator angle. So for determining the angle elevator and chord-wise load distribution, what we have to do? Corresponding pitching velocity must be considered. At that time, definitely pitching velocity must be considered or must be taken care of that one in the maneuvering condition of paragraph 3 and C of this section. So C of this section and this one. The flight condition for in trim and out of trim flight must be considered. So the flight condition also what? Condition for in trim and out of trim means when we are applying the trim and when we are reducing the trim, that also should be considered. So second one is maneuvering balanced situation. Okay. So assuming the aeroplane is in equilibrium and experiencing zero pitching acceleration means that aeroplane is in what? Equilibrium condition and there is acceleration, that pitching acceleration is zero. So there is no pitching acceleration. The maneuvering condition A through I on the maneuvering envelope must be investigated. A through I, all the parts that must be investigated. Okay. So this is maneuvering pitching condition. So this one was maneuvering balanced situation. Maneuvering balanced situation, and third one is what? Maneuvering pitching condition. The condition listed below must be investigated. So while finding this one, these things must be checked or must be investigated. First, pitch control displacement maximum at VA. That VA position, what is the control displacement? That maximum control displacement. The aeroplane is assumed to be in level flight when the cockpit pitch control is abruptly moved to achieve extreme nose-up pitching acceleration. So just here, the aeroplane is assumed to be in level flight when the cockpit pitch control. So when cockpit pitch control is what? Moved to achieve extreme nose up. Means up to what the nose up pitching will be there. They achieve that one, means nose up pitching acceleration. So when that cockpit nose will go for or will experience the highest or maximum pitching acceleration. The response of the aeroplane must be considered when defining the tail load. So this response of the aeroplane must be considered when defining the tail load. So at the tail, how much load is acting, and at that time, what is the response of the aeroplane, that also must be considered. Airplane loads that occur after the normal acceleration at the CG. So airplane loads that occur after the normal acceleration. That normal acceleration is there, and then after that, at the CG exceeds the positive limit maneuvering load. So after the normal acceleration, what happened? At the CG exceeds positive limit maneuvering load. So now maneuvering load in the positive limit it's exceeded. Okay, maneuvering load factor or the resulting tailplane normal load reaches its maximum. Or you can say the positive limit maneuvering load factor increases, or the resulting tailplane normal load reaches its maximum. So normal, what happened? Resulting tailplane is there, that reaches to its maximum. Whichever occur first do not need to be considered. Whoever is coming first or out of these two, that should not be considered. Only the later one will be considered. Okay, now the second part. Okay, that we had seen this one. So the maneuver between VA and VD was checked. So first, the maneuver between VA to VD means in between VA and VD checked. The positive limit load factor prescribed must be achieved by nose up checked pitching maneuver. So already we had seen the pitch positive limit that is generated if that nose is there, that cockpit nose is up. So positive limit load factor prescribed, whatever is there, that must be achieved by nose up check pitching moment. Right. So by nose up checked pitching maneuver. So when that is nose up maneuvering, that time that should be must be the positive limit load should be there. Or in another word, when nose up pitching moment maneuvering is going on, that time the positive load limit factor should be there. Separately, nose down check pitching maneuvers with a limit load factor of 0 G must be analyzed. So when that is coming down, at that time load factor 0G must be analyzed. The flight deck pitch control motion must be used when defining the aeroplane loads. The flight deck pitch control motion must be used when defining the aeroplane load. So when we are defining the aeroplane load, that time flight deck pitch control also should be considered. Okay, so assuming the aeroplane is flying at an any speed between VA and VD, the flight deck, so now just we are assuming in between any whatever is there, but generally, so the flight deck pitch control is moved using the following formula. So how to find the flight deck pitch control is moved by using the formula what? Delta T is delta 1 sine omega T for 0, that T is less than equals to 0 and greater than equals to T max, means T value from 0 to T max only it will be there. Either it will be greater than equal to 0 or less than equals to T max. So maximum up to it will reach up to T max, and minimum it goes up to 0. Now what is this delta 1? So delta 1, the maximum available displacement of the flight deck pitch control in the initial direction. So delta 1 is the maximum available pitch control. Okay, the maximum available flight deck pitch control, that is delta 1. So that is already defined in the initial direction. As limited by the control system stops, control surface stops, or by pilot effort. In that case, what happened? Control system and control surface stopped. Delta T is what? So here delta T is the displacement of flight deck pitch control as a function of time. So that delta T is the displacement of the flight deck. In the initial direction, delta T is limited to delta 1. So that's why here it is 0, right? So in initial case, delta T is limited to delta 1. In the reverse direction, delta T, the displacement of, reverse direction, delta T may be turned at the maximum available displacement of the flight deck pitch control as limited by the control system stop, control surface stop, or by pilot effort. So here this means up to it can go that T max. So delta T can go up to T max. Okay, and in initial condition, delta T is limited to delta 1 value. Okay, so from here T max will be equals to 3 pi by 2 omega. So maximum T will be what? 3 pi by 2 omega. Omega, what is omega here? So here omega is the circular frequency, that is radius per second, of the control deflection taken equal to the undamped natural frequency. So omega is what? The circular frequency of the control deflection taken equal to the undamped natural frequency. That frequency should not be damped. The normally it's that natural frequency should be there, of the short period rigid mode of the airplane with active control system effect include. So what happened? Omega is just, it's a natural frequency, that circular natural frequency, but that should not be damped, means undamped natural circular frequency. How to find that omega? So omega is pi v by 2 va, where v is the speed of airplane at entry to the maneuver. So just before starting the maneuver, what is the speed? That is v, and v is the design maneuvering speed at which it's a or maneuvering speed whatever designed is there. So that is va. So the formula is omega equals to pi v by 2 va, where v is the speed of airplane at entry to the maneuver, means just starting before the maneuver. What is the speed? And va, whatever the design maneuvering speed is there. Okay. So now second, for nose of pitching maneuvers, the entire flight deck pitch control displacement history may be scaled down in amplitude to ensure that the positive limit load factor should not exceed. So in nose pitch up, what happened? That positive limit load factor starts increasing. So that what we have to do? We have to see that one, that positive load factor should not exceed it. Okay. The entire flight deck control displacement history can be scaled down in amplitude to ensure that the normal acceleration at the center of gravity does not fall below 0g. So now that is here what we have to take care of. Their positive limiting load factor should not be increased. Next, the entire flight deck control displacement history can be scaled down in amplitude. So now whatever the amplitude is, just scale down that one to ensure what? Normal acceleration at the center of gravity does not fall below 0. So they should have the normal acceleration where at the center of gravity does not fall below 0 g during nose down pitching maneuver. So during nose down, that should not fall from 0 g, and during nose up, that limit load factor should not exceed. Furthermore, if the aeroplane responds to the specific flight deck pitch, control motion does not meet the prescribed limit. Okay, if the aeroplane responds to the specified flight deck pitch, control motion does not meet the prescribed limit load factor. So that time what happened? That whatever the prescribed limit load factor is there, that is not meeting. The following flight deck pitch control motion must be used. That time what happened? This one. So delta t equals to delta 1 sine omega t for t less than equals to 0 and greater than, t greater than equals to 0 and less than equals to t1. Okay, then delta t is delta 1 when delta t becomes delta 1 for t, that t is less than, greater than equals to t1 and less than equals to t2, and delta t equals to delta 1 sine omega. So just here delta t sine omega of t plus t1 minus t2 square. Sorry, t2, not t2 square, t1 and t2 is there. Okay, for t less than, t greater than equals to t square and less than equals to t max. So just anyhow, whatever this t should be less than the t max. So means in between 0 to maximum only the value of t can be there. Right. So this is for delta t. Okay, in terms of when it's 0 to t1. Then delta t only 1 when t is that, when t is greater equals to t1 and less than equals to t2, and then another delta t is what? Delta 1 sine omega, and this t will change with respect to this one, so that becomes t plus t1 minus t2. Okay, where t is greater equals to t square and less than equals to t max. So now let's see what is t1 here. T1 is pi by 2 omega. T2 is t1 plus delta t, means by what amount its time is changing. So t1. So you can say t2 is equals to t1 plus pi by 2 omega. T max. So T max is what? T2 plus pi by omega. So T2 is what? T1 plus, T2 is pi by 2 omega plus delta t. So T1, okay, T1 plus, T2. So this is pi by 2 omega plus delta t. This is value of T1, and plus, okay, this one plus delta t that is there, and pi by omega. So this will be the t max value. See once again. What is T1? T1 is pi by 2 omega. T2 is T1 plus delta t. Hence T2 is just putting this T1 value. So T1 value is pi by 2 omega plus delta t. So this is our T2 value. Now T max is what? T max is T2 plus pi by omega. What is T2? So this one. So T2 is pi by 2 omega plus delta t plus pi by omega. So this will be the T max. Okay, you can further simplify this also. So that will be that 2 omega. This will be pi plus delta t into 2 pi omega plus 2 pi. So that we can write that as 3 pi plus 2 pi omega into delta t by 2 omega. So this will be the T max in terms of omega. Okay. So now let's see how this will vary. This is the delta between the difference of T1 minus T2. So here, or simply from here, this also we can say that delta T equals to T2 minus T1. So from here, just see how it's a start. This is the flight deck control deflection delta versus time graph. So just see here, once it reaches to this point, that is the maximum, delta 1, that now this becomes the maximum. After that, it's a constant, and once it reaches to T1, so from T1 it's a constant, and once it reaches to T2, then again it's start decreasing and going down. So that time it becomes minus delta 1, and here this is the T max. So up to this only that value will be there. So first condition is what? 0 to T1. So for T, 0 to T1 up to this, right? Then here this is only delta. So just see here, this is a curve. So that's why it's varying from delta 1 into sine omega t. Sine, whenever sine is there, that curve path will be there. So now this is varying curve. Now next, what is delta t? That is simply delta 1. That is the constant value. From where to where? The t value is from T1 to T2. Means it's a greater than equal to T1 and less than equals to T2. So up to T1 to T2, the value will be delta 1. That is constant. Now, once you will, this is third part. So delta t is delta 1 sine omega into t plus T1 minus T2. Okay. So again, this will be the curve. So after drawing this, what we are getting, this is the curve for the third. So this is for the third. So here this is first, second, third. So this part is for second and this part is for first, the curve. So after putting the value, this curve is drawn. Okay. So this figure is what? Flight deck control deflection versus time graph. Now let's see what is delta t here. So delta t is the maximum period of time necessary to allow the prescribed limit load factor to be achieved in the initial direction, but it need not exceed 5 seconds. So their value is only the 5 max, that should be less than 5 seconds. But what is that? To allow the limit load factor to achieve its initial direction. Right? That is the delta t. When the flight deck pitch control motion is affected by system input. Okay, so when the flight deck pitch control motion is affected by system input, what system input is giving? For example, a stick pusher that can operate at high load factor as well as 1G. Okay, so this is why the effect of those system must be considered. Means when the flight deck pitch control motion is affected by the system input, that effect also should be considered. Next, airplane load that occur after the following times are not required to be considered. Airplane load that occurs after the following time. So after some certain time, whatever is there, after that, whatever the load is acting, that is not required to consider. At the time at which the normal acceleration at the center of gravity falls below 0g during the nose-up pitching maneuver. So at the time which the normal acceleration at the center of gravity, right? So at the center of gravity falls below 0g during the nose-up pitching moment. That also not required. So this is the case which is not required to consider, because this is under fifth point. So these two are the things which is need not to consider. The second one is the time at which the normal acceleration at the center of gravity exceeds the positive limit load factor during the nose down pitching maneuver. So the time at which normal acceleration at the center of gravity exceeds the positive load limit during the nose down pitching. So just see, in earlier say in nose up, that the positive load limit should increase, and in negative nose down 0g should be there. So but here that is there. So that again, if it's increasing the positive limit load during the nose down pitching maneuver, then we will not consider that one. Now next is gust load. Gust load on aircraft can have a negative impact by increasing aerodynamic and structural load. So gust load having a negative impact, but we cannot control the gust load also, because gust load already we had seen what is the gust load, that is the air load. So when the aircraft is flying, that time because of the disturbance of air or maneuvering, whatever the load is acting, okay, so that we cannot control by increasing aerodynamic and structural load. So we cannot control that one, but we can control our system. We can make the such aircraft which experience less gust load. How that one? By doing aerodynamical and structural load. So by impact increasing aerodynamic and structural load, causing a structural deformation. So because of that, what happened? structural deformation and reducing flight dynamic performance. So because of that, the structure is getting deformed and reducing the flight dynamics of performance. So whatever the flight dynamic performance is, that also is getting reduced. Okay, so just see the first. So this is here the vertical gust, how this is acting, V, and U. Okay, so this is the U, how this will be there. Okay, this is the vertical gust, this U is acting here, so you can see. Okay, the resultant of this, and this is this one. So second, again a streamline velocity is coming, and now this is there. So just see here in this figure, you can see this is somewhat inclined, that curve, and that's why it's named as here. The resultant, this is again VE, V, so V, so this is U, that is gust load, and this is called the lateral gust. So just according to the direction how the gust load is acting, that is the name. Okay, the third one is head on gust. So here V is there and U is also along this one, is in the same direction it's sitting. So VE, V and U. So V and U in the same direction. So that's why it's a head on collision type, or you can say, or in another word, head on gust. So let's see again how it's acting. Based on that only their name is there. It's acting in this case, first one, right, vertically, right. So all the resultant of this one, that VE and V is vertical. So that's why their name is vertical gust. In this case, the here, this one, that are inclined, some lateral position is there, right? And so V and VE, okay, will give what? So just here in that, in the negative direction, V is here the upward side and V this one downward side. So V, but here V is in upward and V is downward. So just see along the V to VE direction will be there, right, for gust load. So from V to VE direction of gust load is there. So V to VE is gust load. Right, now third one is what? Head on gust. So in this case, what happened? Just see here the V from here, what we can see, from V to VE the direction is there. So now from here this is V, and from here somewhere it is started, that U also, and it's heading towards VE. So that type of gust load is called as head on gust. Clear? Okay, now next is monocoque and semi-monocoque structure. The term monocoque refers to a structural technique in which stresses are reacted to by a thin membrane or a cell of material rather than a collection of beam. So let's see, the term monocoque refers to a structural technique in which stresses are reacted to by a thin membrane. Instead of directly stresses like this one is there. Okay, so instead of acting stress directly, they are not acting. What they are doing, they are just upper part of the skin of this one is this one. So first stress will act on this one, and then this skin will distribute the stress in all other members. So either two things are there, just apply the direct stress to the member will experience the stress, or second one, so when skin is experiencing that load, instead of that member directly, skin is experiencing, and that skin will distribute or share to the other's member. So if when skin will share to the other member, that is called the monocoque. Means first load is acting on the skin, and now skin dividing. Just opposite way, semi-monocoque means somewhat load is acting directly to the member, and in some case, in some part, they are acting on the skin of that one. So such structures are being stiff and light, because now the skin is very thin and very flexible also. So once load will act on the skin, they will distribute. So that structure is what? Lighter and stronger also. So bending stiff and light, making them ideal for weight sensitive vehicles such as aeroplane. So this option is what? Making sensitive, that wherever the weight sensitive things are there we can use this type of structure. Which type? Monocoque. A monocoque structure has a high likelihood of buckling or crippling, as demonstrated by a person standing on top of an empty aluminium beverage can. So on an empty aluminium beverage can, or you can say just an aluminium coke, have you seen that coke can is there, right? In that, what happened? By a person standing on top, once you will stand on that one, and then you can see that also is okay. Monocoque structure has a high likelihood of buckling or crippling, so they will buckle and cripple, the buckling and crippling load will be higher. That how you can find this stand on the empty aluminium can of Coke or any cold drink. The empty container can support a grown man. The empty container can support a grown man, but with the person standing on it, push the side in which the pencil and the can will be compressed in the blink of an eye. Right? The empty container can support a grown man. That empty container will support. But what happened? But with the person standing on it, push the side in which a pencil and the can will be compressed. So like how we can compress the can? If suppose this is the can, right? Once we will stand over there, then what happens? This will get compressed. Same like pencil also. Pencil is there. Once we will start, that will get compressed. So depending upon how standing on that one. So even in blink of an eye, that will get compressed. Because of this instability, an internal support structure that resists these failure modes must be added. That's what happened. Now this is the structural can, that can of Coke or any beverage. Okay, if suppose here or anywhere like this one, if anyone will stand, what happens? This will get collapsed. This will get compressed. So now to overcome that one, what happened? If suppose we will fit here like this one. Now what happened? After standing on this one also, this support will hold this structure because inside nothing is there, that is hollow. So once we will put a one, forget about to stand on that one. Even if you will put 200, 300 gram also, then it starts compressing. So now to prevent that one, what happens? Just put some member in that one to support that one. Okay, compressed. Okay. Because of this instability, an internal support structure that resists these failure modes must be added. So now what we have to do, we have to add some internal structure in between that, and even after that, that can itself is very having the very less weight. But if you will add the internal structure, then even man can stand also, and it will not get compressed. A support structure of this type is typically made up of frame, bulkheads, stringer, and lunge rods. So whatever the structures are there, that are generally called as what? Frames, bulkhead, stringers, and lunge rods. Okay. Same monocoque construction refer to this combination. So once these things will add it, so right, monocoque is just into follow this one. Right now, just in between, add something to support this structure. Then that is called as what? Semi-monocoque, because the whole thing is not, because we added some support to prevent the failure or to compression. So that is called the what? Semi-monocoque structure. Means the structure in which that skin is transferring loads to the other member, and that is from the inside you can see that is hollow, and in that is called monocoque. And in monocoque, if we add the structure like frames, bulkhead, stringer, these things, then same becomes the semi-monocoque. Although the support structure increases the overall weight of the configuration. So it's obvious we will add the support structure that will increase the weight of the configuration. It retains its light and stiff characteristics while reacting to applied load. But what happened? It retains its light and stiffness characteristics. So though after adding, their weight will increase, but it retains their light and stiffness characteristics even after applying the load. The introduction of the monocoque structures was a significant step forward in the development of aircraft structure. So this one helps, okay, for the development of the aircraft structure. As previously stated, such structures respond to applied load in the skin. So what happened? They are applied to the skin, right? Okay, let's see, by a thin membrane or a cell material rather than collection of them. So in monocoque, only the thin skin, hence the term stressed skin construction. Or another word also you can say, because that load is acting on the skin only. So a stressed skin construction. Okay. Difference between monocoque and semi-monocoque structure in aircraft. In aircraft, that is different. So just say, the monocoque structure relies on its outer shell to withstand stress and load. So in monocoque, what happened? Only outer shell is there. There is no frame inside, or there is no supporting member inside. So it totally relies on how much stress will act. Whatever this thickness or their capacity is, up to that it can sustain, and later it will get collapsed or compressed. But in case of semi-component, what happened? That semi-monocoque, whereas the semi-monocoque structure relies on an internal skeleton. So whatever the frame or skeleton inside we added in that one of the support and braces to keep it's a safe, rigid and strong. So in monocoque structure what happen? It depends on the internal structure instead of only base cap. The next difference is to help distribute stress evenly along the fuselage during flight. The vast majority of pressurized aircraft are semi-monocoque. So to just distribute the what happened? The vast majority of pressurized aircraft are semi-monocoque. So pressurized aircraft are of semi-monocoque type. Some helicopters, on the other hand, use a monocoque structure to maximize internal space in the flight compartment. So in the internal, because that helicopter size itself is very small. In that, if they will add the structure, that supporting structure, then what happens? Even that space becomes even lesser. So to prevent that one, they are just simply using the monocoque structure so that inside they have more space and they can keep more thing. Okay. Now stress is in thin and thick cell. Thin cylinder first. That's it. What is thin cylinder? Closed vessel are used to store pressurized fluid. Right? That is of the closed pressurized fluid. If the ratio of cell thickness to the internal radius is less than 1/10, the cylindrical vessel is known as a thin cylinder. Means whatever the thickness of this is there, just here, the ratio of cell thickness, okay, to the internal radius is less than. So how much this thickness is there? This thickness only, okay, divided by, or just take example. Okay, so this is the thickness. This thickness divided by what? The internal radius. So this is the internal radius, right? So this thickness divided by this thickness. Okay, if that is 1/10, okay, less than 1/10, then we can say cylindrical vessel is of thin cylinder. The stress distribution in this cylinder is assumed to be uniform across the thickness of the wall. So across the thickness of the wall, right? Okay, that stress is assumed to be uniform. So just see again. Okay, the thickness of this one, suppose this is the one, so here this is the thickness, right? So this is thickness, and from here it's the center, right? You can see from here to center. So this distance, okay, this thickness divided by this radius will, if it is less than 1/10, then you can say that is the small, that thick, sorry, that thin metal is known as thin cylinder. Okay. Stresses in a thin cylinder, how that stress is acting. So just when the wall of a thin cylinder is subjected to internal pressure means suppose inside some fluid is there, so that fluid will also exert the pressure on the wall of the container, right? A cylinder, it experiences two type of tensile stress. So when that container is filled from the inside, so internal also, that pressure will act, that fluid will act pressure on the internal surface of the cylinder. So first one is hoop stress or circumferential stress. Hoop stress or circumferential stress, which acting on the circumference of the cylinder. And second one is the longitudinal stress. Okay, so here, this here. So this shows how. So here you can see this one along this it's showing. Okay, now here just see. So along this one sigma 2 is acting, along this one, like along this sigma 1 is acting, and along this sigma 2 is acting. And how that is there? So just see here. That is a thin film subjected to stress. So sigma 1 along this it's acting, you can see. Right? And sigma 2 acting along this one. Right? Or here in that, just in the closed loop, here is the sigma 2. That here, because this is a cut part, so here hoop stress will not act. Okay, so but here this one is the closed one, so here, okay, that will act. Now stresses in thin and thick cell, circumferential stress or hoop stress. So first, what is circumferential or same circumferential or hoop stress is there, which is acting along the circumference. Consider the following thin cylindrical cell subjected to internal pressure. Okay, the cylinder has a tendency to split into two parts due to circumferential stress. So this one is there, right? Because of the circumferential they will try to split into two parts. So after splitting, what happens? They will become like this one. So circumferential or hoop stress we are denoting by sigma 1 or F1 or sigma C. So don't get confused with this one. Just remember what you are using. So circumferential hoop stress either as sigma 1. In this figure, we use sigma 1 as circumferential stress. Okay. And sigma 2 just acting here. That is the longitudinal stress. Or here also I should use this sigma 2, right? And this is sigma 1. So this is your hoop stress or circumferential stress, and this is your longitudinal stress. Okay. So if the force due to fluid pressure exceeds the resisting force, so if the force due to fluid pressure exceeds the resisting force due to circumferential stress, bursting will occur. So what happened? Force because of the fluid pressure exceeds whatever the resisting capacity is there, means whatever the internal fluid is applying pressure on that container or cylinder, that exceeds their holding capacity or their standing capacity, then what happens? That will burst. As a result of the force equilibrium, what happened? 2TL sigma C. Sigma C stands for circumferential, that is equals to P into dl. So now from here sigma C will be equals to what? P dl by 2TL. Okay. Now for the longitudinal stress, consider a thin cylinder subjected to an internal pressure as shown in figure. Now this is for longitudinal. So this will act along this one. So now this will act along this one like this. Instead of this was the circumferential one. Now this will act like this. So this is a tangential one. Okay. So now tangential or sigma 2. Sorry, that tangential only the longitudinal stress. So force from the equilibrium, again just apply the equilibrium. So sigma L into pi dt equals to P into pi by 4 into d square. So now from here what happened? Pi will get cancelled. Okay. D will get cancelled one. So after that what is left? Sigma L equals to P d by 4 t. So this will be the longitudinal stress. Okay. So just see quickly type of structural joint. So when that skin fuselage is any components are connected with the two different things. So fuselage, like example, fuselage is connected with the stringer and frames. Wings is connected to the stringers and wing ribs. So for this type of metal, when metal aluminium alloy are there, we are preferably using the riveted joint method. How to that one? So riveted joint also is difficult because of that discontinuity of that substance where we are putting, because after making hole only we can put the rivet. So now that part becomes discontinuous. Okay. And in that also the option is if this one, where it should be placed and how it should be placed, if that is done by the experienced person, then only whatever the safe load is there, that can be achieved. Otherwise we cannot achieve the same or that safe product. Then that is procedure. Okay, the first, how to apply that one? When the control surface is there, that should not be missed. The control surface applied by the pilot should be what? Then only they can apply once that is control surface displacement more than becomes the pilot control system. The next is the corresponding pitching velocities must be considered when determining elevator angles. And so for finding elevator angle and chordwise load distribution, the pitching velocities must be considered. Next, we have seen maneuvering balance situation. How to maneuver during the maneuver, how to balance that one. So how what with assuming aeroplane is in equilibrium and experiencing zero pitching acceleration. That time only we can say that is balanced condition. The maneuvering condition A through I on the maneuvering envelope must be investigated. So what are maneuvering pitching condition? So these things are need to be verified. The first, pitch control displacement, the maximum at VA. The aeroplane is assumed to be level flight when the cockpit pitch control is abruptly moved to achieve maximum. So these things need to check before that one that I already explained. Then symmetric maneuver load. In that the condition is what? For the aeroplane, flight deck pitch control using the following formula. How to find that one? So just see here that delta T equals to delta 1 sine omega T for T greater than equals to 0 and less than equals to T max. What is delta 1 here? The maximum available displacement. So maximum available displacement is this one. Multiply with sine omega T, okay, and the T value will be up to what? From 0 to T max. Okay, for that T max is what? 3 pi by 2 omega. What is omega? Omega is circular natural frequency in undamped condition, right? So omega we can say pi v by 2 VA radian per second. What is V here? The speed of airplane at the entry of the maneuver. Just before starting the maneuver, whatever the speed is there, that is V, and VA the design maneuvering speed up to what it can sustain. Okay, so from there again we got this one for different condition. So first one was, this one was a normal one. So just draw the graph. So from here where to where? T is greater than equals to T and less than equals to T1. So just see here delta 1 sine omega T. So that's why sine omega T is there. So this curve is there from where? From 0 to T1, right? 0 equals to and up to T. Now delta T from T1 to T2, or you can say T is less than equals to T1 and T is greater than equals to T1 and less than equals to T2. So in between just only the delta 1 is there, means that is constant. So from T1 to T2, delta 1 is constant. Now the next is delta T equals to delta 1 sine omega into T plus T1 minus T2. Right? This value lies from T2 to T max. So T2 is here, T max is here. So again that sine is there, means that will be the curve. So now after putting, we got this one. So finally from these three equations, this curve can be drawn. So where what is T1? T1 is pi by 2 omega. T2 is T1 plus pi, T1 plus delta T. Now put here this one, you will get T2. What is T max? T2 plus pi omega. That already I showed solved. What is delta T? The minimum period of time necessary to allow prescribed load limit factor to be achieved in the initial direction, but it need not exceed 5 seconds. Means that should be less than the 5 second only. Okay. Now these things are the maneuvering load condition. How and what to check? What are these things we have to consider? Right. Then next is the gust load. Depending upon how the load, that gust load is what? Air load. In air, when the load is acting, that is called only the gust load. So now V is in this direction and V is in this direction. Then VU will be the vertical, and that U is acting vertically. So the name is the vertical gust. Now here you can see U is acting in this direction, like some inclined one. So VE and V. So just see here V is in this direction and V is in this direction. So V to VE, the direction of gust is there. So similar way here, this is V, this is VE. So direction of V will be, means direction of U will be from V to E. So that is downward. So this is called the lateral gust. The third one is what? Head-on gust. So again V, VE and V to U, this is there. So let's see, from V to VE direction. So from V to VE direction of U will be there. So this type of gust is called as the head-on gust. Now monocoque and semi-monocoque structure. The term monocoque is what? Their skin type will be there. A thin membrane or cell experience the force. Means they experience or they will collect all the winds. So that is the monocoque. Semi-monocoque is what? When we attach some structure, additional structure to support that monocoque. Means monocoque is there. We are attaching some internal frames, structure or anything in the monocoque, then it becomes the semi-monocoque construction. Okay. Then differences. Okay. Monocoque, only the outer cell is experiencing. Semi-monocoque, internal frames also. So it depends on the internal structure also. Okay. Then to help distribute the stress evenly along the fuselage during flight, the vast majority of pressurized aircraft used semi-monocoque. Helicopter using what? Some helicopter using monocoque, so that they will have a larger compartment so that they can keep the things. Then stress in the thick and thin cylinder. So thin cylinder, just anything is there, stress is acting based on that. How? If internal radius and the thickness, the ratio of thickness to internal ratio is 1/10, or you can say if the internal radius is 10 times more than the thickness, then we can say that as the thick cell, otherwise it's a thin cell. Okay, so that there are two types of stress, hoop stress or circumferential stress. first one, and second one is the longitudinal stress. So hoop stress are circumferential. So by the word itself, it's a clear circumferential, which stress acting along the circumference here, along the circumference, that is called the circumferential, or you can say here. Okay, so along the circumference, that is called the circumferential stress or hoop stress, and that which one is acting along this one, that is called longitudinal stress. Right? Now circumferential stress is acting along the circumference, having tendency to split into two parts. So after this, because of the internal pressure, whatever the fluid is inside, they are exerting pressure on the skin and they are trying to split into two parts. So after splitting, here two parts is there. Okay, so that is the circumferential stress. In that case, what happens? Just at the equilibrium, 2TL into sigma E equals to P into D. So from here, what we will get? Sigma C equals to P dl by 2T, okay, L. Right? Where T is the thickness, L is the length, okay, D is the diameter. So now L get cancelled. So P D by 2T. So sigma C will be equals to P D by 2T. Okay. Now in case of longitudinal stress, again that will along the axis it will act along the. So for equilibrium, sigma L into pi dt is equals to P into pi by 4 d square, because along the axis it's acting. So now again sigma L equals to what? Just here, pi will cancel. So sigma L equals to P d by 4 t. So this will be the what? Longitudinal stress. Okay. For this you can refer what? THG Maxon aircraft structure, which is your textbook also. Okay, in 5th edition, 6th edition, or whatever edition, almost the theory is same. So you can just refer that one. So if you have any doubt, you can just comment on the video, or you can ask me directly so that I can clear your doubts.
Like, share and subscribe. Hit the bell icon for more updates.